Hello, everyone. Thank you all for coming. I'm so excited to be here. Budapest is a beautiful city. I'm from San Francisco. My name is Imad Elyafi, and I'm a software engineer on Web Core Experience team at Pinterest. And one of the projects that I've been working on last year is React migration. And today, I'm going to tell you a story about our journey to React. We'll take a look into challenges we faced and techniques we used while migrating Pinterest profiles to React. If you have any questions, please make a note, and I'll be happy to answer them in the end. So today's presentation is broken into 4 major parts, and the first one is about why we decided to migrate to React at all and not any other library. The second part is about how we had to prepare our infrastructure first before we were able to build something in React. The third part is about measuring the impact, and this is a pretty important part because during migrations like that, you may introduce bugs or break something, and you'll never know if you're not measuring the things that you're building. And the last part, I will share you the details, how our life and engineering life has changed after adoption of React. So first of all, why we had to move away from the existing framework at all. And the existing framework, Denzel, which was built in 2013, served us well until a certain period of time. But nowadays, it's outdated. It's very common to many other frameworks that were introduced during that time, 3, 4, 5 years ago. And it's based on object-oriented JavaScript paradigm, and it uses component-based hierarchy. So one of the most common questions is why we decided to move to React and not to Angular, Ember, or Meteor, or anything else. And on this slide, you can see a list of requirements that we had to our new framework. And we want to have a framework with a large developer community. And React has a huge developer community, and we would like to take advantage of this developer community. Another requirement is design patterns. And React is very compatible with our legacy stack, and it makes the migration to many other frameworks much easier. The third requirement is solution for isomorphism, or so-called universal rendering, and I will tell you later why this is so important for us. And another requirement is performance, and React is well known for its performance benefits. You probably heard about virtual DOM and reconciliation algorithm and so on and so forth. And the last thing is developer experience. And this is our old legacy stack, and you might have something similar in your project. We have Python Django web server, Jinja Renderer on the backend, Nunjucks on the client, and it served us well, but being on board with all of these, like Module Bundler, Redux, Just Unit Tests, and many other tools and features, has completely changed the way we develop our modern web apps. So just to give you an idea of scale that we operate at, we have 200 million of monthly active users, which is more than the population of the biggest country in the world, Russia. We serve more than 150,000 requests per second. And since we constantly ship new features, we run hundreds of experiments, we can't just simply freeze our product development in order to rebuild the new web app from scratch in React. And while it's relatively easy to build a new web app in React, changing a service, migrating a service that is constantly changing is like changing engines of an airplane while mid-flight. So how many of you have tried to rewrite your web app from scratch in any other framework? Okay, we see a lot of hands, and I tried to do this before, and ended up in a situation when I had old web app, which is still in production, and many, almost hundreds of engineers were completely changing it, adding new features, and I had a new one, which is still under development, and I had to port all these features back to the new one. And it's like a constant race condition, not the best situation to be in. So now, how can we avoid this? And the only way to avoid this is to rewrite our web app part by part while the rest is still run by the old framework. And now we're coming to this idea of so-called hybrid app. It's an app where we have two frameworks and they coexist together for the time of the migration. And thus, our engineers will not have to write everything at once. They will be able to migrate it piece by piece. So now we want to ask a question. How can we make a hybrid app? And a very first thought, maybe it's not that complicated, but let's take a look at the list of the all possible challenges. And the very first challenge is that React is obviously a JavaScript framework. And how many of you have JavaScript on the server side? I can see a little bit of hands, but obviously not everyone. And having JavaScript on the server side is not a very common thing, but having JavaScript in Python, PHP, or Java, or many other server-side languages is very rare. It's obviously not common at all. So in order to enable our JavaScript rendering on the server side, we had to prepare infrastructure first. And some of you may ask a question, why do we actually need so-called universal or isomorphic rendering? And there's two reasons for that. First of all, our engineers, they will not have to write their templates twice, so we're saving their work and time. And the other reason is SEO. And even though nowadays search engines, they can execute JavaScript and parse page that is rendered on the client side, we run a bunch of experiments. It's still better to serve the initial markup as a string, as an HTML string. So the second challenge is rendering React components inside of the old framework. And while React is pretty flexible in terms of rendering, as long as you can provide a container DOM element, there still might be some challenges. And for example, what if your template files are stored, what if your templates are stored in separate files? Or what if your template's using a custom-made template language? And such example is Jinja templates in Python and Nunjax in JavaScript. So the third challenge is dealing with the old resources. And more likely in your project, you have a resource layer which does all the communication with the API. And probably you want to reuse it at least for the first period of time, unless you want to really rebuild everything from scratch in React, and you'll have two web apps, as we discussed before. So dealing with the old resources is another challenge. And the last challenge is, how can we make sure that newly created UI and components, they're actually performing better than the old ones? What if we introduce a bug or performance issues and something is going wrong with the users? So here we outline our 4 main challenges, and now let's dive deeper into each of those. And before, let me give you a high-level overview of our web app architecture. As you can see on this slide, there is nothing crazy. We have a client-side web app, Python Django web server, and we have backend API. And when a user agent sends a request to the server renders HTML with Jinja Renderer in Python and sends back all this HTML to the client, which spawns a bunch of requests for CSS, images, and JavaScript, and many other assets. It initializes the app, and after that, all subsequent requests are handled only for retrieving the additional data. So there is no more subsequent renders on the server side. All the renders are happening on the client side. And because of that, we had so-called isomorphic rendering. So now let me give you a little bit of a context about Jinja rendering engine in Python and Nunjax in JavaScript. And these templating languages are very similar, almost identical. And because of that, we had so-called isomorphic rendering. And the only one caveat in this approach was that we had to have 2 sets of utils. You can see there is one set utils and libraries for Python and another one for Nunjax in JavaScript. Not the best approach because you have to run tests and do all the things that are not the best. How many of you are familiar with Nunjax or Jinja at all? Not that many people, but that's fine because I'm going to go into a high-level overview of this templating language, and it's pretty common, similar to many other languages. On this slide, you can see a small code snippet. We are initializing 3 variables, very common to many templating languages. On this line, you can see that we are executing our template. And if Creating a name is empty will render hello guest, welcome to Pinterest. And finally, on this slide, we are rendering a module called home feed. And module is a function call. In JavaScript, it will be converted to a function call in JavaScript, which will find home feed module, and it will render for us, passing all the options as the properties. Does it look familiar for you at all? Any React people? So it seems like this architecture fits very well into each other. This is a React code snippet, and we reading properties, we're calling home feed module, we're passing all the options as the properties as well, and home feed is another function call in React. So this looks very, it seems like this architecture fits very well into each other, but the only one issue is that JavaScript and Python is not a common thing at all, or any other server-side language. Because of that, as a very first step, we enabled non-JS rendering on a standalone Node.js server that enables JavaScript rendering on the server side. This will unblock non-JS rendering, and our engineers will not have to rebuild the whole thing at once, but they will be able to migrate incrementally, rewriting our web app piece by piece. As a bonus, we can reuse the same utils and libraries, so there is no more duplicating libraries, only in JavaScript, no more in Python. So now we have a plan for our migration. At first, we'll migrate from Jinja and Python non-JS on the client to non-JS on the server and on the client. And now let's take a look how our rendering used to work before we introduced Node.js Sidecar. As I mentioned before, our templates are structured as trees. A root module can have children module, and children modules can have more children modules. And a renderer pass traverses the tree, rendering each of these nodes and combining them into resulting HTML. So a user agent sends a request to the Python Django web server. Then we send a request to the backend API in order to retrieve the initial data for the template. And we start rendering our templating tree. So we render it as far as we can go until additional data is needed. At this point, worth to mention that this process is CPU blocking, so nothing else can be rendered in this process. And this happens serially. At this point, we request additional data from the backend API. And we continue our rendering as far as we can go until additional data needed, and we're requesting additional data. And in the end, after the whole template is rendered, we're sending the resulting HTML. Now, let's take a look what happened after we introduced a Node.js sidecar. As you can see, the whole architecture is very similar to what we had before, but now we have NGX proxy layer for load balancing, and we have a set of Node.js workers. As it was before, we're sending a request from the user agent, and we're requesting the additional data from the API. After that, we're sending a request over network to our Node.js server in order to render our non-JS template. So here, where it becomes different, we're starting rendering with Node.js server over network, and thus we were able to enable JavaScript rendering on the server side. As it was before, it renders the template as far as it can go until additional data is needed, and at this point, it returns back partially rendered template as a response. And our Python Django web server requests more data from the backend API. So now we repeat the process, but the only difference is now we can send multiple requests, one per each subtree, in order to parallelize rendering process. And we rendered it as far as we can go again, and this process is not CPU blocking anymore. So after both subtrees are rendered in parallel, we send back independent responses to the Python Django web server, and we continue process again and again, requesting additional data if it's needed, we send multiple requests, and we continue rendering until the tree is fully rendered. And at this point, we send the resulting HTML to the user agent. So if you can see, the approach is very similar to what we had before, but now we're rendering JavaScript templates on a standalone Node.js server. And you can use this approach in many different languages. We used it in Python, but if you are in Java or PHP, or you have something else, even like Cold Fusion, if someone is using it still, then you can use the same approach. So now, at this point, we're able to solve our first challenge, and we can render NodeJS templates on the client and on the server. And now we can go ahead and solve our second challenge. Let me provide a little bit of context about the old framework, Denzel. Denzel is very, very similar to many other frameworks that were introduced 3, 4, 5 years ago. It's a component-based framework and uses object-oriented inheritance approach. And on this slide, you can see 2 NodeJS statements, and one of them is old Denzel module call, and another one is new React component call. And as I mentioned before, module is a function call. It basically converts to JavaScript call, which will render for us old Denzel component. The same applies to the component call. Component call is another function call, but it falls back to React rendering. So in order to empower our engineers to migrate our service incrementally, we tweaked NodeJS code, and we introduced a new keyword component, which represents a bridge between Denzel and React. So once NodeJS renderer meets component keyword, it will render Denzel-React Bridge instead. And on this slide, you can see a simplified version of Denzel-React Bridge, which is a Denzel module which will render for us React component. Let's take a look how it works. So once the component is added to the DOM, it will read its own options, and it will figure out the name of the React component that we want to render. And it will render this component, passing all the options as the properties. The rendering will happen in its own container DOM element. So this is pretty simple, but pretty powerful technique, and you can use it in many other JavaScript libraries if you want to migrate from one library to React and you want to use the same libraries together during a period of migration. Some of you may ask a really good question. How React will reuse the server-side rendered markup on the client side? And this is a really cool feature of React, because once the HTML is rendered on the server side, React will automatically add a checksum to it. And after the web app is initialized, React will re-render the HTML in its own virtual DOM. Not a real DOM, but virtual DOM. And will generate another checksum. And if these checksums are the same, that means that we can reuse the existing HTML and will not have to change the DOM elements at all. This is pretty important for many performance optimizations, and also it reduces UI flickering that you might see when DOM is changed after JavaScript is initialized. I think it's one of the really cool features of React. So now, since we can render React components inside of the old framework, we can deal with the old resource layer. And more likely in your project, you have Ajax library, or library that is built on top of Ajax request that does all the communication to the API for you and serves all the data from the server to the client. And probably, at least for the first period of time of migration, you really want to reuse this library. And for that purpose, we used harder components as adapters. If you don't know, harder component is a very powerful technique that helps you to reuse components logic while remaining components composable. It's a function that takes a component and returns another component. I know it may sound a little bit confusing, but let's take a look at the example, and I think everything will be clear. So on this slide, you can see on the left side, It's a HOC with resource that helps us to communicate with the API and with the old resource layer. And on the right side, you can see the example of usage of HOC with resource. So what happens, on component mount, when the component is already in the DOM, it will send a request to the resource layer. And once the data comes back, it will change its own state. Thus, it will re-render its own component, and it will trigger rendering of the child. This is pretty simple but pretty powerful technique that helps a lot in migrations like that. And you can use it for many other things, not only for dealing with resources, but this one is the main one. For example, if you have some experiments layer or something else, you can always make sure that the newly created React components and architecture are always in sync with this layer. So now we can render Nunchucks on the server. We can render React on the server on the client. And now we can move forward and solve our last and fourth challenge. So now we're talking about UI experiments, and this is the most exciting part for me. With more than 200 million of monthly active users, we have to roll out things very carefully because we have to make sure that our newly created UI is actually performing better than the old one. And for that purpose, we use Gatekeeper A/B testing framework. And if you have something similar in your project, it's super handy. Normally, A/B testing frameworks are used to compare different UIs and see how they behave and measure the data and impact. But you can use these frameworks as well for migrations or refactorings like that. So on this slide, you can see there is a very simplified version of forking logic based on experiment check. And if user is in React experiment, then we render newly created React component. And otherwise, we fall back to the old Denzel module. Now, let's take a look deeper at the experiment setup. You can see component tree or module tree on the right side. And this component tree, at some Denzel node, you can see that we are forking our experiment logic. And the whole right subtree is still rendered in Denzel, but the left one is in React. So worth to mention that once a node is converted to component call, all its children and descendants are necessarily in React. Basically, there is call of React inside of Denzel, but there is no call of Denzel inside of React. And this is done on purpose because it helps you to move faster, and also it would be a total mess if you start calling React inside of Denzel, then Denzel inside of React, and vice versa. You really don't want to do this. Because of that, we had to convert our components from the very leaves, moving to the very top. And we call it bottom-up approach. Also, it's worth to mention that you probably want to run your experiments at maximum per page level, and you don't want to compare your old web app to the new one. Otherwise, you'll have too many factors affecting your data, and you'll never be able to figure out why you have metrics drops or why you have maybe metric improvements. Also, it's worth to mention that you really want to run your experiments exclusively. And otherwise, you'll have the same issue because different experiments will affect the same metrics. Later on, you can log into your experiments dashboard and see different metrics. So while we were running migration like that, we were comparing React and Denzel to many different metrics like engagement metrics or error rate, performance metrics, and so on and so forth. On this slide, you can see a screenshot of the dashboard, and you can see there is a bunch of metrics on the left side, and there is a bunch of squares on the right side. The ones that without color, they're actually gray, and it means that there is not enough data to calculate the numbers, so they will be statistically significant. The red ones means there is a drop, and the blue ones means there is improvement. If there is a drop, you probably really want to investigate it and figure out maybe you introduce a bug, or maybe there is a performance issues that are affecting your user. It's important to say that during migrations like that, you may have a bunch of auto tests, unit tests, manual testing, and things like that, but unlikely they will cover all the edge cases. For example, what if in your web app there is something going on wrong in different language? Or what if people with poor internet connection, they having some issues? And it's really hard to catch things like that using unit tests or auto tests or anything else. But A/B testing frameworks and measuring that your data will always give you a signal that something is going wrong and you can start investigating. So Pinterest profiles were the first user-heavy page that we successfully migrated to React. And during React migration, we've seen consistent performance and engagement improvements. For example, metrics like DOM interactive or board page views were up to 20%. And we got this 20% just from changing the gears and infrastructure without actually changing UI at all. I think this is pretty cool, getting 20% from without changing the UI. During migration, our engineers, our product engineers, they were able to continue changing the service, and they were able to ship different features and run different experiments in the rest of the website. And finally, all of these leads to completely new developer experience. Now, we don't have duplicating nunchucks and Jinja libraries. There is no need to learn nunchucks at all. That makes the onboarding process much easier. There is single language on the client and on the server side, which makes life of our engineers even more easier. And finally, we are part of the large developer community, and there is no need in wiki pages. There is a lot of well-crafted examples and documentation online. It's been a long journey, but we're excited to be a part of React community. Thank you, and if you have any questions, feel free to find me and ask me.